The muscular contraction begins with the neuromuscular junction. The neuromuscular junction includes the axon terminal, synaptic cleft, and sarcolemma. The axon terminal includes calcium ions, calcium channels, and synaptic vesicles. When triggered by action potential, calcium channels open, allowing calcium into the presynaptic side of the synapse. The synaptic vesicles contain acetylcholine, a neurotransmitter that causes muscles to contract. The second part of the neuromuscular junction is the synaptic cleft, a small space between two neurons where neurotransmitters are released. The last part is the sarcolemma. The sarcolemma is the cell membrane that encloses each muscle cell. On the sarcolemma are acetylcholine receptors. When opened, acetylcholine receptors allow for sodium ions to pass through and into the muscle fiber. Now that you know the basics of the neuromuscular junction, let's see it in action. The action potential triggers the calcium channel to open, causing calcium ions to enter. These calcium ions then bind to the synaptic vesicles, triggering the proteins to move apart. These synaptic vesicles contain acetylcholine. Once the acetylcholine is released, it is broken down into acetic acid and choline, which binds with the acetylcholine receptors. The opening of these receptors allow for the influx of sodium ions. These ions help with muscle contraction. The ATP then continues along the sarcomere, which we will continue shortly. Next, the choline is taken back up the synaptic cleft and combined with acetic acid to make more acetylcholine. The new acetylcholine are put back into synaptic vesicles. Let's review the basics of what happens in the muscle fiber. The action potential travels along the sarcolemma and down into the T-tubule. This activates the release of calcium ions from the sarcoplasmic reticulum. Next, we have the sarcomere, which contains the following: actin, binding site, tropomyosin, troponin, myosin, and myosin head. Now that you know the basics of muscle fiber, let's see it in action. Once the calcium ions have been released, they will bind to troponin. The troponin shifts the tropomyosin, which will no longer block the active sites on the actin. Here's what it would look like. The myosin head can then attach to the actin by breaking down ATP into ADP and a phosphate, which is labeled P here. The actin then forms a bridge-like bond between it and the active site. The head of the myosin cocks back and uses a power stroke movement to pull back the active sites on the actin, causing the muscle fibers to contract. Each time ATP is broken down into ADP and phosphate, the power stroke movement repeats, moving on to the next active site on the actin. What would happen if your body went into rigor mortis? During the process of rigor mortis, the same process takes place as from before. This example would represent a body that has just died or is currently dying. No process of cellular respiration taking place to create ATP because there is no oxygen. Without ATP, the myosin head cannot detach and the process comes to a stop. The muscles tense up and are unable to release. Thanks for watching.